Hello everyone. Alright, so this is numbers 1 through 4 for our energy test review. Number 1, power. Power is equal to work over time. So if you were to write the equation for power, it'd be W over T. And the units for power are watts. So which can do more work in a given amount of time, i.e. which one has more power, a bicycle or McLaren F1 sports car? Well, the sports car can do more work in the same amount of time, but are they both capable of doing 1,000 joules of work? What if the McLaren F1 only ran for 5 seconds and the bicycle went for 5 days? It's possible for them to both do 1,000 joules of work, but which one's going to do it faster? Obviously, the McLaren F1. So the McLaren can do more work in less time and therefore has more power. Okay, number 2. In this energy unit, we associate friction, surface friction or air friction, with work. Because friction slowing down an object is doing work on the object. So is it positive or negative? Let's think about this. Here's a little hint. Would friction cause an object to go faster or slower? Well, it's going to cause an object to go slower. So is it adding energy to a system or subtracting energy? Well, it's going to be subtracting energy. So is it going to be positive or negative? It's going to be negative work. It's going to say negative work. Alright, so how would that change the kinetic energy in a system? What in the kinetic energy equation would change and how? So if we look at the kinetic energy equation, we have 1/2. Does that change if an object slows down? No. Does the mass change if an object slows down? No. Does the velocity change if an object slows down? Yes. So the velocity would be less. Alright, next. Both object 1 and object 2 have a mass of 5 kilograms. They are both on an 8-meter tall hill. Using the conservation of energy equation, calculate the velocity for each at the bottom of the hill. Well, on the object 1 side, the hill is a lot steeper than the slope for object 2. And we want to know what is the velocity for each of these objects when it's at the bottom. So we know at the top it's got what kind of energy. And ask yourself the 3 questions. Is it above the ground? Yes. Is it moving right now? No. Is it on a spring? No. So we just have potential energy. So we can say our potential energy is mass times gravity times height, because that's the equation. And then we plug in what we know. We know it has a mass of 5. Our gravity is 10. And the height is 8. So when we plug that in, 5 times 10 times 8, it's 400. So we know that the potential energy is 400 joules. Now, it's 400 joules for the object 1 and object 2 because they both have a mass of 5 kilograms. They both are on Earth, so there's gravity, and they're both 8 meters up on this hill. So we know the potential energy is the same. Well, we know at the bottom, it's not above ground anymore, so we don't have potential. It's not on a spring, but right before it hits the ground, it is moving, so we know we have kinetic energy. So, kinetic energy is equal to 1/2 mass velocity squared. We know the mass is 5 kilograms for each of the objects, but we don't know the velocity. That's what we're trying to solve for. So we can actually say that the potential energy we have at the top is equal to the kinetic energy we have at the bottom, right? Because there's no friction, it doesn't tell us that there's friction, so we can say the potential and the kinetic are equal. So we know the potential energy is equal to 400 joules, because we already calculated that. Let's do this for object 1, okay? So we have 400 joules equals the kinetic energy. So we get 1/2 5 v squared. So if we divide 400 by 1/2 and 5, we could get v squared by itself. So let's go ahead and do that. We take 400 and divide by 1/2, and then also divide by 5. It's the same as dividing 400 by 2.5, because 1/2 and 5 here equal 2.5. You get the same number either way. But we get 160 equals v squared. So just to find velocity, we just take the square root of 160. And we end up with a velocity of 12.6 meters per second. So the velocity of object 1 is 12.6 meters per second. Alright, so let's move on to velocity, or object 2. Alright, object 2 has potential energy of 400 joules at the top. And we know that the potential energy at the top is equal to the kinetic energy at the bottom, right? So we know that PE equals KE. And we know that since it's 5 kilograms and it's 8 meters above the ground, we have 400 joules of potential energy. So we could say 400 equals the equation for kinetic energy, which is 1/2 mv squared. And we know that our mass is 5. So we get 400 equals 1/2 times 5 v squared. Well, okay, time out. How does this equation compare to the equation we had right here for the first object? Alright, you'll notice they're exactly the same. So when we solve for velocity, what do you think we're going to get here? We're going to get 12.6 meters per second. Alright, so object 2 is going 12.6 meters per second at the bottom as well. So how do the velocities compare? They're the same. But object 2 will take longer to get to the bottom, but both objects are going to be going just as fast at the bottom. Okay. So number 4, where does the roller coaster have the most energy? So I think what it meant to ask is either potential or kinetic. So we're going to go ahead. Well, honestly, it has the most energy at all these different places because conservation of energy tells us that we don't create or destroy energy, and if we assume there's no friction, then the energy doesn't change. Let's go ahead and say, where does the roller coaster cart have the most potential energy? So it has the most potential energy at A because it's the highest above the ground. And then G would be next, so the second most potential energy would be G. The third most would be B. The fourth most would be F. Do you see how A is a little bit higher than G, and G is a little bit higher than B, and B is a little bit higher than F? And then fifth most potential energy would be C. Sixth most would be E. And seventh most would be D. So when our potential energy is the highest, the what is the lowest? When our potential energy is the highest, what's this object doing right now? Do you think that it's going very fast? At maximum height, at maximum potential energy, our kinetic energy is the lowest. And here, when our potential energy is the lowest, our kinetic energy is the highest.